going to show how we obtain kinematic equations of the motion. Let me start with this slide. Right now, one object moved to the right. So our coordinate system is x, for example. You can say s or a, whatever you want, you can put your coordinate system. And once you set the coordinate system, this should be your x, and this is your reference. Then as a function of time, the position of your object will change. So that's what this plot shows. Your position x, is keep changing as a function of time, but the rate of change is not constant. Sometimes it rapidly changes and going a little bit slow and so on. Depending on different time, you define each different position. This plot shows the average velocity. Average velocity is determined by the displacement divided by the time difference between 2 points. So here, between time 1, time 2, which is delta t, is the interval between time 1, time 2, and during the delta t, the position change is delta x. So the average velocity is delta x divided by delta v. This is the velocity average. As I told you, the velocity is the displacement per time. It's the measure of the rate of change in the position. And in here, if you make the interval is very, very small, then you can put delta t goes to 0. Okay, then this becomes the definition of derivatives. So dx over dt, but if you make delta t too small enough, then that can become the definition of derivative. So becomes instantaneous velocity at a given time. So right now dx over dt, so the time rate of change of your position becomes the instantaneous velocity. If you take derivatives of your velocity, then that becomes the acceleration, because acceleration is the rate of the change of the velocity. The unit of the acceleration is meter per second square, because your acceleration is 2 times derivatives of your x. So that's why this one becomes the meter per second square. Your velocity is delta x over delta t, so that unit is meter per second, but acceleration is delta v over delta t, so m over s, and unit, another time unit is s, so this one becomes the meter per second square. So these two equations, derivatives, are fundamentals for kinematics. Right now I put those kind of vector superscript. As long as we talk about translational motion, for our convenience, sometimes we omit those kind of superscript. Sometimes we just simply write down ds over dt. So in the previous slide I just used x instead of s. So let's say just use the x, and a is dv over dt. And here, if you rearrange these two equations, so from here, my dt is equal to dx over v. So I replace dt with dx over v. Yeah, in here, dv over dx over v, then dA over dx over v is equal to dv. So a dx over v dvd. So from these two equations, we can make another kind of formula equations, but this equation is not independent from these two, because we generate this equation from these two equations. We can just write down in here. So this is 1 and this is 2 and this is 3 kinematic equation. So let me write down here again, and A is dv over dt, and then although we do not use a lot, sometimes we use this equation as well. Then from here let's assume your acceleration is constant. So I can write down acceleration is constant, so which is dv over dt. So ac over dt and dv. From here, let's take integration. Okay, let's just take integrations from time 0 to a certain time t, and then when time is equal to 0, our initial velocity is v0. So this is v0 and some velocity here. This is constant, that's why AC and just time t minus 0 is equal to v minus vo. So your velocity equations becomes your initial velocity plus AC t. So these are our first kinematic equations of motion. That means if you know the initial velocity and acceleration, then you can predict the velocity as a function of time. Then let's use this one. So we know what the v is. So the v is equal to dx over dt. So we replace the v with this one. So the v0 plus act is equal to dt should be dx, like that from here. Then let's take an integral this one too. So let's say from 0 to a certain time t, when time is equal to 0, let's say our initial position is x0, so x0 and x. Then if you just take integrations, then this one, say you can write down this integration like that. Then this is constant, v0 is constant, so that will be the v0 t plus ac and t and dt. So it should be, this one is 1 over 2 t square and minus 0, because this is here 0, which is x minus x0. So from here we have we got another equation. So your position is equal to your initial position plus the v0 time t and 1 over 2 ac times square. So this is second kinematic equations of motion. So what this one says is, if you know the initial velocity, initial position, then if you know the acceleration, then you can predict your position x as a function of time. And how about this one? So what's the use of this one? So we assume that A is constant, AC, and we can take integrations like that. we assume that our initial x naught, so when position x is x naught, your velocity is v naught, which means this is v naught and v and x. Then AC is constant, so AC x minus x naught, and then this is 1 over v square over v naught square, like that. So this is 2AC x minus x naught v square and v naught square. So actually this one, if we know initial position, initial velocity, then you can relate your position to the velocity square if you know the acceleration. So this is just another kind of kinematic equations of motions that allow us to relate your position and velocity. Then let's look at this example. A particle travels along a straight line to the right with the velocity where t is in second. What is the position acceleration of particle when time is equal to 4 seconds? Okay, so this one just asks you what is the position and acceleration of the particle when t is equal to 4 seconds. So position is this. We can use these equations. However, there is a catch here, because when we derived these equations, we assume that the acceleration is constant, right? But if you look at this question, the velocity is the time of functions. When you take a derivative of your velocity over dt, this is 4 and 6t. So this is your acceleration. So acceleration is function of time. So acceleration is not constant. That means our derived kinematic equations of motions cannot be applied to this example. So can we use these equations? No, we cannot use this one. And these are just good for when your acceleration is constant. Then how we solve this one then? We just rely on these two fundamental equations. Your velocity is the derivative of your position, and your acceleration is derivative of your velocity. We just rely on these equations. So our velocity was given, so that's 4t and minus 3t. That is your velocity. That is equal to your position dx over dt. Then you can just integrate this one from 0 to 4 seconds. Okay. But before you put those for the finite time, you can just use the variable t, and from 0 to x. So if you do the integrations, this one should be 1 over 2 t squared, and this one should be 3 over 3 t cubic is equal to x. So if I write down a little bit better way, and this one should be 2t squared and t cubic. So this should be your position equation. Okay. So right now I want to find the position when time is equal to t. So when time is equal to t, you can get the x. And then this one asks you accelerations. We already get the acceleration here. So when time is equal to 4, your acceleration is minus negative 20 meter per second square. Right? So your acceleration negative. So your object actually is in your object is being deaccelerated. So this slide shows what we derived from these fundamental equations. From here, we take integrations under the assumptions that the constant is constant, acceleration is constant. That we got we obtained the three kinematic equations of motion. Then we can expand these equations into curvilinear motion. Curvilinear motion, that means your particle, instead of moving in a straight line, your particle just follow those kind of curvilinear path. Okay, so we can expand these equations to apply these equations to describe those curvilinear motion as well. Imagine that this is, let's say, your coordinate system like that, and then you just launch an object, so your object is kind of going up and going down like that. Okay, so let's say this is my x and this is my y, and this is a ground. Okay, then I want to describe the motion of my curvilinear path using the kinematic equations of motion. Just imagine that at a given time, let's say object reach at this position. Just imagine that this is my position. Let's say this is my position function. Okay, so my position function is function of time, and then your position functions can be broken into x and y component, sx I and syj. Sx means, if you look at this one of x position, and then you can just break this one into your y position at any given time. If this one changed each position later like that, then also you can think about your position vector or position function as t. This is xsi and syj. Then this could be your sx, and this could be your sy. So basically, even though this is curvilinear motions, if you break the position into x and y components, then everything just have two scalar value, x position and y position. So we just care about x position and y position. Okay, and then accordingly we just pay attention to x directional velocity, y directional velocity, and x directional acceleration, y directional acceleration. That means if we think about the velocity of this ball or object, so when this one goes follow this kind of path, our velocity should be like, let me just use different color. Let's say this is velocity at a given time. Then you can also break your velocity along to x velocity and y velocity like that. Because this is a two-dimensional space, that's why any kind of vector, either velocity or acceleration, you can kind of break down into x directional velocity and y directional velocity. You can just project your velocity into x and y. Also, if you want to analyze the x accelerations, you can project acceleration onto x component and y component. That's why when you analyze the curvilinear motions, we can break down into x and y components and apply kinematic equations of motion to x and y separately. Okay, if I show you the equations again, so we are going to use this equation, right? So let me just try to bring this one to here. Then if I just apply this one to x component and y component separately. Okay. Then my the velocity of x component will be the initial of velocity of x component, and then a certain acceleration of x component time t. Okay. And then how about the position? My x component position will be x component of initial position and x component of velocity of x time t, and 1/2 x component of velocity x and t square. And this equation too. So x component of velocity square is equal to x component square of initial velocity square, and then x component of accelerations and x component s, x component of initial. But think about it. So when you, for example, launch the ball to in this way, the ball is going up and down. Then once the ball is released from your hand, and there's no acceleration along the x direction, because once the ball is released from your hand, there's no x directional force acting on this ball. Right? That's why in this particular example, in a projectile motions, actually there's no any x directional velocity, right? So this one should be 0, and this one should be 0. So surprisingly, in this kind of projectile motions, when you launch a ball, then x directional velocity is always constant, as long as we can ignore the air resistance. How about the y directional? So y directional velocity is equal to initial y directional velocity plus y directional acceleration time t. Then in this particular example, what could be the y directional acceleration? The gravitational acceleration, right? So that's why we can just replace this one is negative g. Why is a negative? Because I make the upward is positives, but gravitational acceleration is pull your object down to the ground. That's why this one should be negative. So I put the negative here. And your y directional of position is your y directional initial position, and then y directional time t, and also this is 1/2 t square. And this one too, the last one, third equation, y directional velocity is equal to y directional initial velocity and 2g, and y directional position minus y directional initial one. Okay. So as I showed you in the projectile motions or curvilinear motions, you can analyze the motion x and y components separately and apply these equations to each x and y, and then use these kinematic equations of motions accordingly.